So let's take a look at the class templates. Class templates is nothing really special, but this is because you've already learned function templates. Of course, they're very similar, but there are some differences too. So there's this concept of instantiation in the same, well, in the function templates will also have the same thing. Now, what actually happens with class templates is, let's just say, here's an example of, let's say we're using the vector from the standard library. By the way, there's a typo here, but this is a vector. So the standard library provides a vector class template. And that vector, let's say it takes a parameter type. That's called a T. And that is basically the type of the elements. And so if you, in this class template, you have basically this is holding on to a vector of elements of a type T. And every time you use a vector by specifying the parameter type, let's say you want to use it with a vector of int, and then in that case, the compiler is going to generate a new definition that will be based off the template. It will create a concrete definition with the type T substituted with int. So in this case, you have a vector of elements of a type int. And similarly, if you provide the template type argument to be a string, and then what you have is you're going to have a new definition that will give you a vector of elements of a type string, and so on. So this is basically saying the classes are instantiated. There are instances of the template, and the template it's like the recipe. It's not an actual class. So your class definition is generated from the template. And how do you define a class template is again similar to function templates. In the very beginning, you have a template keyword followed by angle brackets. Inside the brackets, you have the template parameters, and then which is followed by a class definition. Except this is not exactly a class definition. It's it's almost like a class definition, but it's filled with the template parameters that's used inside the member definitions of the class. And the template parameters, this is actually the same situation with function templates. There are primarily, well, there's actually 3 different types, but primarily we'll focus on the type parameters and non-type parameters. And the type parameters, typically you start the type parameter with a keyword called type name. You can use class, which is the same thing, but anyway, the book has a preference to use type name because we don't, this, because a T may or may not be a class. This doesn't have to be a class. So in fact, this can be pretty much any type. It can be a fundamental type, could be a reference or a pointer. And then you can also have non-type parameters. We have seen, obviously, and used quite a bit, right? So the standard array takes a non-type parameter, the size type, for the number of elements, right? And so, of course, it can be any fundamental type, it can be an enum as well. It could be also reference or pointer. Okay, so there's a wide range of things you can use here. And of course, the len type parameter is almost like a function parameter, right? Uh, so the type parameter is a little different. This is we're having the type as a parameter. And there's this very important principle that needs to be explained a little bit. Uh, it's called the dry principle. What is the dry principle? Dry stands for don't repeat yourself. Well, it's self-explanatory, right? And what it really is trying to say is every piece of knowledge must have a single, unambiguous, authoritative representation within the system. And in the case of essentially we're talking about a program, essentially for a particular functionality or um, unit of logic, unit of a code, and that should not be repeated. Essentially, don't try to copy paste. That's one thing. Secondly, if you notice there's a significant similarity between different blocks of code, perhaps one is dealing with an int, the other one is dealing with double, right? So we have kind of in the case of a function template, we use that. So you can then make a template that can handle different types with the same kind of code. So that is just an example. The language provides multiple facilities to help um, basically implement the dry principle. So for example, use functions that, let's say you have, that's the thing I call copy paste, because the exactly same kind of code, you have this in multiple places, and then you should put that into a function, and that function is reusable, right? So in these different places where, why do we do that? Because if you have the same code in different places, and then one thing is certain, now the program is going to evolve. You're going to have to change your code. The code will change. And when you do need to change that piece of code, now it's, let's say it's replicated in multiple places, then it's very easy to forget to change all the places. Okay, so it's a um, you know um, that's one reason. The other thing is also when you're really writing software, you will be required to write tests. Now, if you have the same kind of code in different places, then you will have duplicate tests as well. It's kind of just more unnecessary burden that you have to write new tests for that same kind of code. So if you reuse the same code that's already been tested, or you just then write test once, right? So there's multiple reasons. And then you can obviously use the templates, so we know function templates, class templates, exactly to, that's also a main mechanism to extract commonality out of the blocks of code. Could it be a function? Could it be a whole class? And then we also have studied the inheritance and the basically the OOP technology, the OOP techniques. The OOP techniques also is another mechanism to allow you to extract similar code into perhaps into a base class, and then you may have derived classes there um, where you have the similarity factored out into a base class. And of course, there's many other techniques. These are just some of the major ones. And there are a few idioms that we want to talk about when it comes to just a decent class design. You're going to encounter that quite a bit. And so it's almost like, that's like how you do these things, and it's just no brainer. And so you do these things the right way. So the const and the back again idiom, what is this about? Essentially, when you have a member functions, you will find yourself having to write member functions. One of them is the const version. It's a const member function where you don't change the object. And then you may also have another version of the same function that is non-const, where you're allowed to modify. You can put that return value on the left-hand side of your assignment, let's say. So one primary example, it would be the subscript operator. And let's take a look at that actually right now. Let's say we have a simple array class, and it's like a wrapper around an array, a primitive array. So we have a array class, and want to emulate that subscript operator. So we'll provide that subscript operator. So there's a const version and there's a non-const version, because the const version, you can basically, that's for the read only. And then you also have a non-const version. Here's the const version. This is a const subscript operator that we are overloading and to access the elements in the array. And then you have a non-const version. And so the input of a non-const version, you don't somehow just copy paste the things that you have already in the const version. And so here, what you do is essentially you, by doing the casting, and then you can reuse that const version to implement your non-const version of the same member function. So that's really, this is kind of a template to do that. So you have arguments of this member function, and so you have the same thing pass on, but except here you want to invoke the const version. How do you invoke const version? So you have to essentially cast this pointer into a const reference first, and then you invoke basically the const version of the same function, and then you cast that back to a non-const return type, right? So that's really what it means, the constant back again idiom. And so that's really the example right here is you cast by using this standard utility function. This is in the utilities header. The utility function adds const that essentially you're casting that into a const reference object. And then by using the subscript operator here, you're accessing this function, the const version of the subscript operator, right? So then that will return a const, basically is a const reference, right? So then what we want here, though, in this non-const version, we want a non-const reference. So what you do is then you use the const cast operator to cast that result back to a non-const reference. Okay, so that is really fairly common, and doesn't necessarily just appear here for this particular example, but this idiom you'll find useful in many different places. And then there's another important idiom. It's called the copy and swap. And copy swap is a exception safe way of dealing with modification to an object. And there are 3 steps. And the first step 1 is to copy the objects, and that copy operation may throw an exception. So it may fail. And then second step, now if it fail right here, that's fine. So, exceptions thrown out, but your object that you wanted to modify, that hasn't been touched, right? So it's no problem. And then, so that exception that was thrown during copy, that could be handled some places. And if it's not handled, eventually the program will crash, right? So that is okay. If it's handled, you can carry on because these objects that you're trying to modify is not corrupted. Now, once you have made a copy, and then you just go modify the copies. So the modification of the copies may also throw in exceptions. And that is okay. If the exception is thrown here, then you just abandon the copies. The copies will be this, you know, reclaimed, right? When it gets out of scope. So these are the local automatic objects. And so again, same thing, the object that you wanted to modify hasn't been touched. And then so the last step is now you've got a copy that's ready with all the modification you wanted. Then you do a swap with your current object, better whether they're the same type. And so now that's why you can swap. Then you swap it so that your object that you want to modify, you're just you take that from the copy that you prepared. And so this swap operation, typically you don't want to throw an exception here. So uh, the idiomatic way is to implement the swap as a separate function. And that function should be marked no except. Okay. And take a look at an example here, actually. So this array, let's see, the array has also a, now copy assignment operator. So we know the compiler can generate D for one, but sometimes D for one is not good enough. And in case of this array class, we have to write our own. And we know the copy constructor and the copy assignment operator, they need to be done. Essentially, they go together. They're like a pair, and because they are the ways to make a copy, and to implement the copy assignment operator here, actually, we're going to leverage the first step of a copy. That is, we're going to use the copy constructor here, right? So you see, we are using leverage and another the logic in the copy constructor. We're not duplicating anything. That's again the drive principle. And then that's really the step here to make a copy. Well, here actually the modification actually is not even necessary here. We're essentially this is just in the simplistic case that, well, we'll see another example where you'll see the actual modification there. But again, then in the end, you do a swap. Now, what does swap entail? You swap the member variables, okay? So the standard library actually provides a swap function, which is actually a template, function template. And you can use this swap your, for example, in this case, you have and this elements, which is a type T or pointer to T. T is of course, is a template parameter. So we're swapping the pointer, and then we're also swapping the size, which is a size type, I believe, right? So you can just use that and then implement your swap function, and then you use that swap. So that's kind of how that's done usually. Now, there's this idea of specialization of templates. And the specialization, there are actually two flavors. You can do a full specialization. Specialization, what does it mean? Specialization means that you are going to, now in the case of explicit or full specialization, you'll see, let's say we have a primary template called is void. And this is void actually derives from the standard false type, which is a simple class that allows you to evaluate the essentially this just gives you the value of this. This essentially just gives you a class that will allow you to read a value which is just true. And then you'll see how we're going to use this. Actually, there's a test program right here. Anyway, so this is the base class here, and then we'll have is void. And then what we can do is we can actually specialize for a particular type. And then this particular type here is called a void. Okay, void is a type, it's a special type. And so by doing it this way here, and you actually provide the specialization with an angle bracket just behind the class name here, but then the template now becomes empty angle bracket. The angle bracket is still needed right here. And in this case, that just means that now the t has been assigned a value, which is a void. And so this is actually no longer a template. This is actually a concrete class definition. Okay, because there's no more in the type is complete, so to speak, right? There's no placeholders. But this is still, of course, related to that primary template, but this is a specialization of that template. In the case of a full specialization or explicit specialization, and you're actually defining a class. And in this case, actually, I'm showing an example what you can do with it when you're doing when you're specializing a template here. You can change things up. Like for here, we're changing the base class to a true type. Okay, so what does that mean? This is an interesting way of doing things here. So what you see here, basically, if you provide any other type other than void, right? See here, we're using char here. Let's say we are using this this class template. We are specializing with the char, and then basically there's a value member. This is a member variable that actually just it's a constant. It just means this is for the false type is false, for the true type is true. And then what this allows you to do is essentially now you can say you can do a test on this particular type, saying is the char type void, right, which is false. That's why it's deriving from the false type. But then if you supply void, and now this is actually a true type, so this value will be true. Okay, it's a constant. It will be just true. How is this useful, right? How is this useful? This can be used to actually to test a type. Like, if when you write templates, you can use things like this. Well, the standard actually defines a lot of this utilities to test the features of a type. Now you have a template T. Now, what exactly is T, right? You may say, well, I want to check if that T is a void type or not. Maybe I do something different when it's a void, right? So we're going to talk more about this when we get to talk about concepts and the constraints on the templates. So far, right now, with our template parameters, we're not putting any constraints. It's, a consumer of this class can provide whatever, right? But then whatever provided, it may not work. We may have an assumptions that are being made that this type has to satisfy certain requirements so that this class is designed to work with that kind of classes, but not with everything, right? Okay, so we'll get to that later on. And then you can also do partial specialization of a template. When you do partial specialization, because it's not a full specialization, right? So there's still some placeholder types, or parameters, non-type parameter or non-type parameter. There are things that are still, placeholders. So that in that case, when you do that, you're still getting another template, which is still incomplete type. You have a primary. So let's say we have a primary template A, which takes a three parameters. You got two, type parameters, and then there's one non-type parameter. Okay, so I, that stands for as an int non-type parameter. You got T1, T2. And then in the first case here, we are, specializing the part of it. And so what we do here is see, we have T and pointer to T. Okay, and then so we still need to take one type, one particular parameter, that's T, In this case, the T1, T2 are somehow related because they actually, one is the value type, the other one is a pointer to type. They're the same, a pointer to that value type, right? And so we have made a little change here. We're saying, T2 is a pointer, but also pointer to the same, to object of same type as T1, right? So this is a type of specialization. And this still remains to be a template. It's not a concrete class definition. And then we may also, let's say here, this situation, we say T1 is a pointer, but which is not the same. The pointer object type is not the same as T2, right? So again, this is just another type of specialization. You can, specialize from a one type to say a pointer type. And so here is another situation. Let's say, well, we're gonna fix T1 to be int. We fix I to be 5, which is a non-type parameter, integer. And then T2, we say, well, we now actually gonna take a pointer. So this is another specialization. You see there's only one placeholder parameter here. The other ones are fixed, are resolved. And then that's the same thing. Okay, so just showing you different flavors of a specialization of a template. Now, we're going to take a look at an example that will demonstrate much of the stuff that we're talking about. And this example is basically showing a simple stack implementation. Now, of course, when you have a real need for stacks, you should just use the standard library, which has a stack in the stack header. Now, for this example, so what is a stack? Stack is a ubiquitous data structure. It's a basic data structure. It's very useful as well. And in the case of a function call, you have a function A calls function B, which calls function C. And then whenever you call function, and the runtime prepares the context for the function call, like the arguments, right? The location of the function definition, and those kind of things. And then those objects, that context of a function call, is put onto a stack. So in the order, when you say get out of so when you throw an exception, you see we'll do the stack unwinding. That's called stack unwinding. Why is it called stack unwinding? Because the function call context are put on a stack data structure. So that's really what a stack is. You're already using stack in many places. You're just not aware of it yet. So a stack, think of a stack of plates in let's say a buffet place, right? You go get your plates out of that whole stack of plates. Usually it's spring loaded at the bottom. And and then when the plates getting low, and then the staff may load up more plates on top. But you can only take a plate off the top or put plates on top of it, right? So that's really what is the primary operation of a stack is you can push an object onto the stack. Then you can pop an object off the stack. You don't get to access the bottom. You can only access the top. That's really what this is about. And then there are many ways to implement a stack. Well, for demonstration purposes, and we're going to just use a linked list. A linked list, we have seen this before, right? So this in pivot version, we'll talk about the box application, a tracking application, right? So we have linked list. Linked list, you maintain a link to the head of the list, and then each node contains the item. That's the object that is the primary object that we're interested in. To maintain the data structure, we will now maintain a pointer to the next node. The nodes are dynamically allocated on the free store, and so they could be anywhere in the memory, and then they are linked together with the pointers. So logically, you can think of them together. So think of logically, all these objects are together in a single stack, but physically, they could be everywhere, anywhere in memory. So that's kind of the linked list. Also, the linked list allows you to, uh, add as many nodes as you need. In the objects is there's no limit. Well, the limit is the amount of memory that's available. Okay, so let's actually just go through the code a little bit, and as an example, let's take a look at 17.4a, and let's just look at this stack definition here. So the stack definition, this class actually is a class template. And this class template is one of the simplest templates, obviously, which takes a single type parameter, and then we label it T, and which is a customary. Usually, you just do a T. T is short for type. And of course, there's this customary constructors and destructor, and then you have the copy constructor. You have the copy assignment operator. Then you have the swap function. Because we're going to use swap to implement this as we saw the copy and the swap idiom. So you have a member function that does the swap, which is no except. It will not throw exceptions. And then the primary operations on the stack, you have a push and pop, right? And then you may also have another function that checks if the stack is empty. And then because we're building a linked list, we need a node class. And here we're just putting this as a nested class in the private section. There's because the consumer of the stack class should not even be aware of this existence of a node. This is purely internal data structure. So this is a private. And because this is a private class, there's really no need to put this under the private member variables. Usually we say, well, member should be private, right? Yeah, you can use private, of course, but then it doesn't really make much difference here inside this class because this is a nested class in the as a private. So we're gonna need to access these variables in stack class, right? The node is a nested inside a stack, and so so here we have a simple constructor which hold on to this item. And then we'll also have this pointer, which is by default initialized to be null pointer. Okay, this is the 0 initialization here. And so that's why we're not seeing this, setting this to null pointer in the constructor. So this is already initialized. Okay. And then outside of the node, this is in stack. The stack will hold on to the head. We need to remember where the head is, which is essentially in the stack data structure. We're saying that's the top of the stack. Okay, so we're gonna always basically insert element at the top and removing element off the top. And so we're using that linked list underlying data structure to give that stack semantic. Stack essentially adds a restriction on that linked list that you can only operate on one end, not both ends. You can't access any element that's underneath the top. So so let's take a look at for example, a couple of things, right? So so again, let's take a look at a swap. A swap here, it's fairly straightforward. We're going to use this. We simply just use the standard swap function, and then to swap these two pointers, right? These are actually simply just pointers, and so that's our own swap member function. And then to implement the copy assignment operator, so we just make a copy, and then we swap. Okay, so that's already enough. Essentially, in the case of assignment situation, we make a copy of the object that we want to assign, that's actually the modification. This is, remember, this is the copy and a modification together because the modification is already presented to the right-hand side of this assignment operator, so which is passed into this function. Okay, so then we do the swap. And then usually the assignment operator returns this object, the current object, so that you can use that to, for some other purposes. For example, you may put that in a for loop or while loop where you use this as a condition to check if that return or whatever is, you can do stuff like that. But then this is just customary. This is the typical way to define this copy assignment operator. And then let's take a look at, for example, the push operation. So the push operation is, think of a linked list. The push operation is basically adding a node to the head. And so this new node we're adding is basically the new head. And so the interface of the class just takes an item, which is the object of interest we're trying to put onto in the analogy of this stack example of a stack of plates. And that's the plate. That's the object of interest. But internally, we'll put that into a node because a node will maintain the data structure as a linked list. So we make a node out of it using this new operator here. Well, and you see, well, why are we using new and delete, right? So we should not be using them. Remember the raw idiom? You're right. So there will be improved version. This is showing the raw pointer, and which is definitely not recommended when you write your own programs. And so, so we make a node, right? And then we basically will set the pointer that points to the next. That will be the next pointer of this new node. It's going to be just the head, right? The current head becomes the next node. So we're adding this node on top of the head. This becomes a new head. So that's why this head pointer now is the same as this node. And so that's really what a push operation is, how it's done here. So I'm just gonna, show you this one, and then there's of course there's a pop operation which is similar, but then when you do the pop, you do want to check if there's any more elements in the stack. If it's already empty, and then you may want to throw an exception. Right, this is one way to deal with it. Throwing exception is appropriate here. And here, notice we're using the standard exception from the library instead of making a customer one. Just call it logic error. You can use a customer one, of course, and sometimes it's not necessary. Now, the other version of this is basically we're gonna just use the write idiom. So why don't we use the smart pointers? Yes, exactly. We should not be using the raw pointer. We should instead use the smart pointers. So if we do use smart pointers, you see the difference here. The next pointer is a unique pointer. And then the head is another unique pointer. Now, since it's a unique pointer, the operation, there's a little twist. Remember the unique pointer, what it is a single ownership, right? So you cannot have another unique pointer object that points to the same underlying object. So if you do need to do stuff like that, and then you need to change hands like of the underlying object, and then you need to use a special function, and then we'll see in a second. So let's take a look at the push, how this is implemented with it now in the case of a smart pointers. In this case, smart pointers, okay, well, now we know how to make a smart pointer, right? Make it unique. Just use the make unique function, and we'll make a node out of this to wrap this item inside it. Now, of course, we still need to fix the next pointer, right? The next pointer needs to point to the next node, which is the current head. So in order for that to point to the current head, we're not assigning the head a unique pointer object directly to it, because the underlying object pointed to by the unique pointer cannot be shared. Now that's why it's called the unique pointer, cannot be shared. So what you can do is to transfer that ownership out of it. You can, by using this standard function called move, and then this will be further explained in the next chapter. This basically allows you to move the ownership of the underlying object. This is owned by, so currently the underlying object is owned by the head member variable, because now we need to assign the underlying object ownership to the next pointer of the node, the new node that we're trying to add into the linked list. So you need to use a move. Otherwise, it will not be, it will be a failure. It will not be correct. Okay. It's just not allowed, actually. So yeah, and then similarly, we node is also a unique pointer, right? So now we need to make it the head, the original head now needs to be assigned this new, it needs to point to the new node. So again, use that move because it's a unique pointer. All right, the single ownership. You cannot have two. Imagine if you don't use a move, now you have two unique pointers point to the same underlying object, right? And that is not allowed. A unique pointer will not allow you to do it. It probably won't even, it won't work. So we'll explain more about this move and what the whole thing is about and how is that achieved. And so that is really what I wanted to share about this class templates. And there's not a whole lot of difference. If you already know the function templates, of course, there's stuff that's unique to classes. So we also kind of learned a couple of idioms. Now let's summarize this chapter. So a class template defines actually a family of class types. A class template is not a class definition. Once it's instantiated, the instantiations of a class template, they are class definitions. So whenever you're actually using a class template with the specific template parameters, and then the actual definitions will be actually generated by the compiler. So that's what I just said. The instance of a class template is generated at compile time. And then you can do implicit instantiation. That's basically you're just using the template. Like, for example, you want to use the vector from the Snell library, use a vector of int. And that's an instance of usage by you defining an object of this class template type. And then compiler says this is going to generate the definition of that particular class, which is the instantiation of the class template. So you can explicitly instantiate a class template, but it's just not very, it doesn't have a whole lot of usage though. So I'm just going to skip this one. And type template parameter can be, well, pretty much any type, right? Fundamental, enum, class, pointer, or reference. The non-type template parameter, typically they cannot be classes. There's an exception. So it's a minor exception that I don't want to explain. You're not going to encounter that much, but again, so if you are interested in the full list of things and what you can use for non-type template parameter, and go to that cppreference.com, and then you'll find, and just search in that website, just search for template parameter, you'll see. So the copy and the swap idiom is not only just used for that assignment, typical copy assignment operator implementation, you use that a lot, but this can also be used in many other places too. So what this does give you is a kind of all or nothing semantic. It will allow you to handle an operation that will not corrupt an object you're trying to modify. So that's also called exception safe. And the copy assignment operator should really just be implemented with that idiom. There's just no excuse not to use it. And then there's another idiom called a const and back again. That is really used for implementing a non-const overload in terms of the const overload. So we have seen an example of that, like the subscript operator that in the array class. And then we do this because, well, the dry principle. Don't repeat yourself. And then an explicit or full specialization, they mean the same thing. Have a class template defines a complete class type. Otherwise, if it's a partial and that what you end up with, when you do a partial specialization, you still end up with a new template, which is made out of the primary one. So that is not a complete class type, it's still incomplete type. And you may use that keyword type name. Remember, that's the one that we'll also use in the template parameter list. And that type name keyword can be used in front of a dependent type name. What's a dependent type? Dependent type really is it's essentially a type that you're using in a template that depends on the template parameter. And so there's things about how the compiler actually parses the code and whether it can recognize what you're using in your code, is that a type or not? And so sometimes the compiler, depends on different compiler, may have different behaviors. They may get confused whether that's a type or not. Well, not that is because not because it's not standardized, just because the implementation, some of the compilers are not complete. That's kind of the main reason, not because the standard is clear on what should be done. So sometimes you may have to add that type name keyword in front of a type to tell the compiler that this is a type. Okay. So that's it for the class templates. Thank you.